NEC Section 210.8b5 mandates ground fault circuit interrupter, or GFCI, protection for all 125 volt, 15 and 20 amp receptacles situated in specific areas within laboratories. These areas include wet or damp locations, locations within 6 feet of a sink, and locations where water use is probable. Consequently, if a sink exists in the laboratory, all receptacles within 6 feet of that sink must have GFCI protection. NEC Section 210.12 stipulates GFCI protection for all 125 volt, 15 and 20 amp receptacles found in dwelling units, which includes dormitories, in areas such as bathrooms, garages, crawl spaces, and unfinished basements. However, NEC Section 210.12 provides an exemption for dormitory rooms not utilized for cooking or lacking a sink, thus excluding them from the GFCI requirement. Furthermore, NEC Section 210.12b mandates arc fault circuit interrupter, or AFCI, protection for all 120 volt, 15 and 20 amp branch circuits that supply bedroom outlets in dwelling units encompassing dormitories. This signifies that all electrical outlets within the bedroom areas of dormitory rooms must be AFCI protected, irrespective of whether the room contains a bathroom or sink. In laboratories, GFCI protection is crucial in areas prone to moisture or water usage. This is because the presence of water significantly increases the risk of electrical shock. The NEC specifically requires GFCI protection for 125 volt, 15 and 20 amp receptacles in wet or damp laboratory locations that is within 6 feet of a sink, and areas where water use is likely. This 6-foot radius rule ensures that even if a user isn't directly at the sink, they are still protected from potential electrical hazards associated with water. The purpose of a GFCI is to detect imbalances in the current flowing through a circuit. If a leakage current, even a small one, is detected, the GFCI will quickly trip the circuit, cutting off the power and preventing a potentially fatal electrical shock. This is particularly important in laboratory settings where sensitive equipment and experiments are often used, and where spills or water exposure are more likely. For dormitories, the NEC provides a specific exemption for rooms that do not include cooking facilities or sinks. This means that in a typical dorm room consisting of just a single room without a private bathroom or kitchen area, GFCI protection is not generally required for the receptacles. The reasoning behind this exemption is that the risk of electrical shock in these types of rooms is considered lower than in areas with water or cooking appliances. However, it is crucial to note that this exemption only applies to GFCI protection. AFCI protection, on the other hand, is still required for all 120 volt, 15 and 20 amp branch circuits supplying bedroom outlets in dormitories, regardless of the presence of a bathroom or sink. AFCIs are designed to detect arc faults, which are dangerous electrical conditions that can lead to fires. Arc faults can occur due to damaged or degraded wiring, loose connections, or faulty appliances. When an AFCI detects an arc fault, it quickly trips the circuit, preventing the arc from escalating into a fire. The requirement for AFCI protection in dormitory bedrooms reflects the NEC emphasis on fire safety in residential settings. Dormitories, with their high density of occupants and electrical devices, are particularly vulnerable to electrical fires. By requiring AFCI protection, the NEC aims to significantly reduce the risk of these fires. The installation of GFCIs and AFCIs should always be performed by a qualified electrician who is familiar with the NEC and local electrical codes. Incorrect installation can render these devices ineffective or even create new hazards. When installing GFCIs, it is important to use the correct type of GFCI for the application. There are different types of GFCIs available, each designed for specific uses and environments. For example, some GFCIs are designed for use in wet locations, while others are designed for use with specific types of equipment. Similarly, when installing AFCIs, it is important to choose AFCIs that are compatible with the existing wiring and electrical system. There are different types of AFCIs available, including branch circuit AFCIs, which protect the entire branch circuit, and outlet branch circuit AFCIs, which protect only the outlets on the circuit. Regular testing of GFCIs and AFCIs is also essential to ensure that they are functioning properly. GFCI should be tested monthly by pressing the test button on the device. If the GFCI does not trip when the test button is pressed, it should be replaced immediately. AFCI should be tested annually by a qualified electrician. In addition to GFCI and AFCI protection, it is important to follow other electrical safety practices in laboratories and dormitories. These practices include avoiding overloading electrical circuits, using extension cords safely, and keeping electrical equipment in good repair. Overloading electrical circuits can cause the wiring to overheat, which can lead to fires. To avoid overloading circuits, do not plug too many devices into a single outlet or extension cord. Use extension cords safely by ensuring that they are properly sized for the load and that they are not damaged or frayed. Avoid running extension cords under rugs or furniture, as this can trap heat and create a fire hazard. Keep electrical equipment in good repair by regularly inspecting it for damage and replacing any damaged cords or plugs. Do not use electrical equipment that is wet or damp. In summary, GFCI protection is required for 125 volt, 15 and 20 amp receptacles in specific areas of laboratories, including wet or damp locations and areas within 6 feet of a sink. GFCI protection is generally not required in dormitory rooms that do not include cooking facilities or sinks. AFCI protection is required for all 120 volt, 15 and 20 amp branch circuits supplying bedroom outlets in dormitories. Proper installation and regular testing of GFCIs and AFCIs are essential to ensure their effectiveness. By following these guidelines and other electrical safety practices, you can help to prevent electrical shocks and fires in laboratories and dormitories. It's important to remember that electrical codes like the NEC are updated regularly to reflect new technologies and safety concerns. Staying informed about these changes is crucial for ensuring that electrical installations are safe and compliant. Consulting with a qualified electrician or electrical inspector can provide valuable guidance and ensure that all applicable codes and regulations are met. Furthermore, it's worth noting that while the NEC provides a baseline for electrical safety, local jurisdictions may have additional requirements or amendments. Therefore, it's essential to check with the local authorities to determine the specific electrical codes and regulations that apply in your area. When dealing with electrical systems, safety should always be the top priority. Taking the time to understand and comply with the NEC and local electrical codes can help to protect people and property from electrical hazards. To further elaborate on GFCI protection, it's crucial to understand how these devices work. A GFCI constantly monitors the current flowing through the hot and neutral wires of a circuit. In a properly functioning circuit, the current flowing through the hot wire should be equal to the current flowing through the neutral wire. However, if a fault occurs, such as when a person comes into contact with a live wire, a portion of the current will leak to ground. This leakage current creates an imbalance between the hot and neutral wires. When the GFCI detects this imbalance, even if it's only a few milliamperes, it quickly trips the circuit, cutting off the power and preventing a potentially fatal electrical shock. The speed at which a GFCI trips is critical. GFCIs are designed to trip within a fraction of a second, typically within 20 to 30 milliseconds. This rapid response time is fast enough to prevent serious injury or death from electrical shock. In contrast, a standard circuit breaker is designed to protect against overloads and short circuits, but it is not as sensitive to leakage currents as a GFCI. A standard circuit breaker may not trip until the leakage current reaches several amperes, which is far more than enough to cause serious harm. Regarding AFCI protection, it's important to understand the different types of arc faults that these devices are designed to detect. There are two main types of arc faults: series arc faults and parallel arc faults. Series arc faults occur when there is a break or discontinuity in a single wire. This can happen due to damaged or degraded insulation, loose connections, or physical stress on the wire. Parallel arc faults occur when there is a short circuit between two or more wires. This can happen due to damaged insulation, moisture, or conductive materials coming into contact with the wires. AFCIs are designed to detect both series and parallel arc faults. They do this by monitoring the current and voltage waveforms in the circuit. When an arc fault occurs, it creates a unique electrical signature that the AFCI can recognize. When the AFCI detects an arc fault, it quickly trips the circuit, preventing the arc from escalating into a fire. There are two main types of AFCIs: branch circuit AFCIs and outlet branch circuit AFCIs. Branch circuit AFCIs are installed in the electrical panel and protect the entire branch circuit. Outlet branch circuit AFCIs are installed at the outlet and protect only the outlets on that circuit. The NEC generally requires branch circuit AFCIs for new construction and renovations. However, outlet branch circuit AFCIs may be used in some cases, such as when it is not feasible to install a branch circuit AFCI in the electrical panel. The selection of the appropriate type of AFCI depends on the specific application and the requirements of the local electrical code. In addition to GFCIs and AFCIs, surge protection is another important aspect of electrical safety. Surge protection devices, or SPDs, are designed to protect electronic equipment from voltage spikes or surges. Voltage surges can be caused by lightning strikes, power outages, or other electrical disturbances. These surges can damage or destroy sensitive electronic equipment, such as computers, televisions, and appliances. SPD work by diverting the excess voltage away from the equipment and safely to ground. There are different types of SPD available, each designed for different applications and levels of protection. Whole house SPD are installed at the electrical panel and protect the entire electrical system. Point of use SPD are plugged into individual outlets and protect the equipment plugged into those outlets. The selection of the appropriate type of SPD depends on the specific needs and the level of protection desired. Regular inspection and maintenance of electrical systems are also essential for ensuring safety. This includes inspecting wiring for damage, checking connections for tightness, and testing GFCIs and AFCIs. Any damaged or worn electrical components should be replaced immediately by a qualified electrician. It's also important to avoid overloading electrical circuits. Overloading circuits can cause the wiring to overheat, which can lead to fires. To avoid overloading circuits, do not plug too many devices into a single outlet or extension cord. Use extension cords safely by ensuring that they are properly sized for the load and that they are not damaged or frayed. Avoid running extension cords under rugs or furniture, as this can trap heat and create a fire hazard. In conclusion, GFCI protection, AFCI protection, surge protection, and regular inspection and maintenance are all essential components of a comprehensive electrical safety program. By implementing these measures, you can significantly reduce the risk of electrical shocks, fires, and equipment damage. Remember to consult with a qualified electrician or electrical inspector to ensure that your electrical system is safe and compliant with all applicable codes and regulations. The NEC guidelines provide a solid foundation, but local codes and specific installation circumstances should always be taken into account. Staying proactive and informed about electrical safety is key to protecting people and property from electrical hazards.